thank you very much. Actually, not very much fiber lasers, more or less in general, mid-infrared technology. The reason is that fibers are not there yet if you want to have a very intense mid-infrared radiation. So I'm sorry for the kind of low quality of the slides that I'm going to present today, but I was quite busy in the last period and I prepared them this morning. So I hope you cut me some slack about that, but we can start. So basically, why it's interesting to have mid-infrared radiation, intense mid-infrared radiation, also for a community like yours dealing with ultrafast studies in interesting systems, actually. So in the mid-infrared, you have, in general, molecular vibrations, rotations. So all these degrees of freedom express energy in the mid-infrared frequency range. But there is also something that goes beyond the standard atomic and molecular optics. You can also start to address very interesting fundamental questions in condensed matter systems. So a lot of magnetic degree of freedoms that are related to correlation of spins between individual atoms in a condensed matter systems. And also correlated system like superconductors. So the superconductivity is related to energy, to an energy scale that is in the mid to far infrared spectral region. In addition, there are also a lot of technological aspects that are extremely relevant because semiconductors, and in particular heterostructures made of semiconductors, have a lot of transitions, inter-subband transition in this frequency range, and plasmonics is moving towards application to the mid-infrared because you have an interesting combination of length of the optical cycle and field enhancement. Now, in general, in the infrared, it's a little bit tricky to define where, you know, the edge between near to mid-infrared to far infrared it is. It's a little bit, you know, it's a matter of a pure definition, and it's practically not very relevant for what we want to discuss here. So what I'm going to discuss here in terms of mid-infrared, and I will be kind of very general in this sense. I'm trying to cover frequencies from basically 2 micron to 1 terahertz, that is 300 microns. The reason is that the technology for generating intense pulses in this frequency range, they are not so different. They are very similar. They always rely on nonlinearity, since there are not many sources that provide short pulses in this frequency range. Basically, if you want to buy a commercial femtosecond system, femtosecond laser, out of the laser, the longest wavelength you can get at the moment, it's 2 micron. That basically it's fiber lasers based on thulium and holmium frequencies as active material. Beyond that, you have to rely on nonlinear optical tricks to generate the pulses where you need them. And to study all these things, in particular to drive matter strongly out of equilibrium, you also want to have intense radiation, not just probe, but you want also to kick matter in an interesting way. So what is the standard mechanism to generate mid-infrared radiation? And of course, it's second order nonlinearity. It's the easiest accessible order of nonlinearity that you can use. And basically, the fundamental mechanism is different frequency generation that we have already seen this morning, thanks to the talk, in particular of Rossio. So this is clearly a mechanism in which you can use 2 inputs to use the nonlinear polarization given by the medium in which you are going to drive this nonlinear phenomenon to obtain at the output the different frequency generation. So this is just an example. If you have a this nonlinear crystal with proper phase matching, 1 micron input, 1.3 micron input, you obtain the difference in frequency generation between these 2 frequencies, you end up with radiation at 5 micron. Okay, so this is a way to access the mid-infrared frequency range. Of course, this has to fulfill all the conditions that are typical for second order nonlinear processes, all nonlinear processes, so momentum, energy conservation and momentum conservation. Now, this process that in a virtual energy levels is depicted on the right side of the slide, it's basically the same process that is employed as generation of pulses via optical parametric amplification, okay? DFG is the fundamental process at the base of optical parametric amplification. The difference is only in the initial conditions and in a matter of definition. So DFG typically is called the process when you have two equally intense input beams and you obtain the difference frequency generation pulse. If one is much weaker than the other, and in particular the 1.3 micron here, could be considered the seed for an optical parametric amplification process. Now, there is an important distinction that I want to make immediately. Typically, in an OPA setting, this lambda2 is called signal, and this lambda3 is called idler. But there is the misconception that the idler is always at longer wavelengths than the signal. That's not the case. I prefer the definition in which the signal is the one that you seed. So if here you just, instead of seeding lambda2, you would see lambda3. Lambda2 would be the idler, the difference in frequency generation that you're going to generate. But the process is perfectly symmetrical. Okay, given this definition, this is the fundamental nonlinear process that you are going to deal for the rest of this talk. And basically, we need an intense pulse that is providing the energy, and then we are going to induce this difference in frequency generation process to generate the infrared radiation, the mid-infrared or far-infrared radiation. And if you are in an OPA scheme, we also have an amplification of the signal in parallel that might be interesting for some application. Now, if we have an additional complication, okay? Because when we are doing this difference in frequency generation process, in particular, if you want to access very long frequencies, but this is true also for the mid-infrared, we have essentially two possible approaches. One that is traditionally, again, called optical rectification, in which we have a single pulse that actually is at the input of your nonlinear crystal, in which what you're going to do is the difference in frequency generation between two spectral components of the pulse itself, okay? And the peculiarity of this process is that technically the lowest frequency that you can generate is a zero frequency, okay? It's a constant frequency that is the result of the traditionally defined optical rectification. Another process, another way to have this difference frequency generation process that is more akin to optical parametric amplification is to have difference frequency generation between two independent pulses, in which then the idler is the result of the difference frequency generation process. And the advantage of this second approach is that intrinsically you're going to have more energy to drive your process. So the process is going to be more efficient in terms of counting photons. Because the more bandwidth you want to achieve with optical rectification, the more you're going at the tail of your spectrum. So you see that, of course, the intensity at the tail of your driving spectrum is going to be lower, the overall energy that you can exploit to drive your nonlinear process. And in terms of just counting the photons, you don't have enough possibilities to obtain this difference frequency generation process. So the interpulse DFG is intrinsically more efficient for multi-THz generation. So again, general from terahertz to mid-infrared. And now, what is if we have this general framework, how can we generate single cycle pulses in the mid or far infrared? It doesn't matter too much. What I'm going to discuss is very general and can be with the proper nonlinear materials ported in the two frequency ranges. So the aspect is that Rosia was already discussing is that you need to have phase matching. The wave vector of the pump has to equal the sum of the wave vector of signal and idler, or frequency 1 and frequency 2 in a generic difference frequency generation process. But the bandwidth of this process will rely on the difference in the group velocity between signal and idler, okay, or the two most read frequencies of the three-wave mixing process. That is proportional to the group velocity mismatch. So if we achieve a condition in which we can have this group velocity matching during the generation of even far infrared radiation, we are going to have intrinsically broadband condition. And then we can expand to higher orders. So also if we match also the dispersion, the bandwidth is going to be even higher. I can anticipate to you that this group velocity dispersion, it's practically impossible in the mid-infrared frequency range, while group velocity mismatch actually can occur. Matching can occur. So this is the exercise. And what we can do as an example, okay, if we have a material that allows two specific frequencies of pump and signal to achieve the broadband frequency generation. So let's imagine in this situation, a pump wavelength around 1.2 micron and a signal wavelength around 1.3 micron. We can drive the process in a way that the idler is at the frequency specifically in which you match the group velocity of the signal. We will see now how you can do that. So, sorry, this actually is a different condition. It's pumping at 800 nanometer and signal, you see the frequency of the signal in micron in the lower axis. So, if we use these kind of materials that are high refractive index materials that were already introduced a little bit before, lithium iodate, lithium niobate, potassium niobate, and their periodically poled variation, we can plot the difference in group velocity between signal and idler in this graph. So this is plotting this difference. And you see that we have few zero crossings. Okay, so we have one zero crossing at 1.6 micron. In this case, we are pumping at 800 nanometer. So it means that the group velocity of the signal and the idler at 1.6 micron is going to be the same. But if the signal is at 1.6 micron, it means that also the idler is at 1.6 micron. Okay, it's half the wavelength of the pump. So this is the one that Rocio was explaining before, the degeneracy OPA. In this condition, actually, you see that the signal propagates faster than the idler. So if we want to build an OPA pumped at 800 nanometer based on this material and seeding at 1.2 micron, it will not be broadband because the idler moves faster than, the signal moves faster than the idler. So the trick here in this frequency range is to build a non-collinear optical parametric amplifier, as already explained. Now, what we care for mid-infrared is instead it's this other point. Okay, we have another point in this graph in which we achieve matching between the group velocity of the signal and the idler, and you see that is at around 1 micron for this material if we pump at 800 nanometer. But if we pump at 800 nanometer with signal at 1 micron, means that the idler is going to move in the mid-infrared around 5 micron. And why we have this condition in which we have broadband phase matching at this frequency range? Well, the point is that we exploit the fact that the dispersion of materials changes its sign. So if we look at the refractive index of any dielectric, we are going to have that we have a maximum of the group velocity that is somehow in between two absorption lines of the medium itself that are going to be in the visible and in the mid-infrared. So the maximum group velocity is going to be somehow in the middle. While we move towards the mid-infrared and the vibrational absorption of the material, the group velocity starts to slow down, and you can have a condition in which you match the group velocity of another frequency on the other side of this curve. Okay, so you can achieve, and in this kind of material, these materials are relatively good to generate mid-infrared radiation in a frequency range between 3 to 5 microns. But the concept that I explained, you just shifting pump frequency and pump frequency, signal frequency, and idler frequency can be transported to reach up to the terahertz frequency range, so to the several tens of microns. Okay, these are some, for example, calculations. If you use an OPA pumped at 800 nanometer based on these materials, if we seed it with these spectra centered between 1 and 1.2 micron, we can easily get broadband OPAs, you see, that are 2000 nanometer broad between 2.5 to 5 micron. Okay, with temporal durations that here are around 20 femtosecond, but at that point we have to compare the temporal duration to the optical cycle at these frequencies. So we are around the 2 optical cycle temporal durations. Okay, and this is how to implement this kind of system. And here there are a couple of details that I want to point out because they are quite crucial, and there are a few tricks that are very important to optimize when doing these kind of things. So if we have an OPA pumped by 800 nanometer, we usually split a portion of the energy to generate a white light supercontinuum in order to be the seed of the amplification. So in this crystal, we are going to have the first difference in frequency generation process that occurs in the form of an OPA, in which we are generating an idler around 3 to 5 microns. Okay. Now, notice one important aspect. This is kept non-collinear. So there are several strategies that can be done here, because I can think about several ways of making this OPA. But there is one important crucial aspect. If I'm doing a non-collinearity, if I'm using a non-collinearity angle between the pump and the signal, the idler is also going to come out from my crystal at a certain angle with respect to the pump. Okay, you see it here. But not only, it's going to be angularly dispersed. So every color in the idler is going to have a slightly different direction of propagation. Okay, so it's going to be spatially chirped. So not very useful for a lot of applications. What is the solution? The solution is either doing the first stage already perfectly collinear, or like we did in this case, you can do a first stage in which you just amplify the 1 micron radiation, okay, to have more photon to drive then a second, more optimized difference frequency generation in the same crystal, in which you see again the pump at 800 nanometer, the signal at 1 micron, but this time perfectly collinear, so that then you can generate an idler at in the mid-infrared frequency range. Okay, why this choice? Well, the point is that usually the first stage of an OPA is a high gain stage, in which you need to focus quite significantly the pump in order to achieve a certain efficiency in the process. Just the divergence of the pump beam and the signal beam would result in a strong dispersion of the idler, because you have to think about the idler as a very short wave vector. So when you build a triangle, okay, the long axis of a triangle will be the pump wave vector. The signal is very similar, so the idler wave vector is going to be very small to join the tip of the other two. And in that situation, the angle of divergence gets multiplied by the ratio of the frequency. So let's say that you have a 1 degree focusing angular aperture in the focusing pump beam. The idler intrinsically will have 5 degrees if you go from 800 to 4 micron, 4 point something micron. Okay, so that's why it's very crucial when you do difference frequency generation in the far infrared to try always to operate with collimated beams as most as you can, because if you have a collimated beam, at that point you are sure that also the idler is emitted in a collimated way, more or less, and it makes much easier to do the next chains of optical elements that are used to then generate do the experiments. These are some practical results. So it's possible to generate really broadband pulses, fairly tunable, depending a little bit on the phase matching conditions. Again, the temporal duration is around 20 femtosecond, but you have to compare these to the optical cycle that you have at these frequencies. When you are in the mid-infrared, you are kind of lucky because you can still do frequency resolved optical gating to characterize the pulses, because you have indium gallium arsenide spectrometer that can collect the second harmonic of mid-infrared radiation. The more infrared you go, the more tricky that is. And typically, the characterization ways that you employ for longer wavelengths employ different techniques like electro-optic sampling that I'm going to explain in a few seconds. Just importantly, this electro-optic sampling technique, now it's thanks to the availability of shorter and shorter pulses in the near infrared, becomes more and more powerful, and nowadays it's possible even to characterize near infrared radiation with electro-optic sampling. And this is a very good advantage with respect to other frequency ranges and other colors, because you can characterize completely a pulse in amplitude and phase with a very low noise. So you can use that information or even to do spectroscopy. If we move to longer wavelengths towards the terahertz, let's say beyond the 5 micron to 10, 20, 30 micron, you start to have, you need to slightly change the overall technology that you use to generate the pulses, but everything is fairly similar. And you can have extremely high peak field that actually are also comparable to what you can obtain in free electron lasers. Keep in mind that free electron lasers were initially employed for the generation of mid-infrared and terahertz radiation rather than XUV. And how to do that? This is, for example, one experimental result in which you can have up to 10 megavolt per centimeter. So we are talking about tens of microjoule in a terahertz pulse. That it's not that trivial to achieve, because you have to keep in mind that energy conservation, it's a problem when you generate beams with photon energy that is extremely small, because the point is that also the number of photons has to conserve, so to be conserved. So if from 100 photons from the pump you generate 10 photons of the idler, you have a 10% efficiency in photons. But if these photons have a much smaller energy, in energy the efficiency it's much lower than that. Okay, so we have to be extremely careful on how we assess the efficiency of our processes. And how to do that, actually, this is why I was showing the two pulses at 1.2 and 1.3 micron, is because if you have on disposal such pulses that you can easily generate via standard OPAs, you can generate via differentiation generation, interpulse differentiation generation in, for example, gallium selenide, very intense radiation that basically reaches one single cycle of the optical radiation with very high efficiency for this frequency range. Okay, so you can have, for example, at 30 micron, a temporal duration of 40 femtosecond. That is exactly how much a single cycle lasts in that range. Keep in mind that this is a depiction done in plotting the electric field, not the intensity of the laser itself. Now, all the consideration that I've done before with respect to 800 nanometer, 1 micron seeding, 5 micron in the class of nonlinear materials that I showed you before, that basically are dielectrics. Okay, in this condition, we are going to use more semiconducting materials. So gallium selenide is a semiconductor. Now the boundary between the definition of semiconductor and dielectric is also quite loose, but gallium selenide is basically almost dark in the visible. It has absorption from the near infrared above. And in this condition, pump at 1.2 and signal at 1.3, we are exactly in the situation in which the idler that is going to be generated at 13 micron, the group velocity at 13 micron in gallium selenide matches the group velocity of the signal at 1.3 micron. So we are going to have this broadband phase matching that allows to have the generation of single cycle pulses. in detail how it's done, a setup like that. To be the most versatile possible, because of course you want to generate single cycle pulses. But it's not obvious that you can have a material that pumped at the frequency of your driving laser works. So for example, if you want to generate broadband pulses around 13 microns, pumping at 800 nanometer, there is no way. There is no material that allows that. So the maximum flexibility is to develop a full system in which you have the usual titanium sapphire, or maybe nowadays ytterbium high power femtosecond lasers, typically region amplifiers, in which you drive independently 2 near-infrared parametric amplifiers, high power. Maybe each of these can be multi-stage. And then in parallel, with these 2, you tune them in order to define the perfect difference in frequency generation that provides you the broadest frequency range in the frequency at the frequency at which you want to operate. And then you do this difference in frequency generation in the nonlinear material, that in our case is gallium selenide here. And then you can do spectroscopy. You focus it on your material, and you can do, in this specific case, electro-optic sampling to detect the pulses generated, so the mid-infrared radiation. And this can be done also with extremely high precision. So you can also do delta T over T. So you can measure differential signals in electro-optic detection. So you can measure amplitude and phase in the response of your sample, whatever it is, when you apply it to spectroscopy. Okay. Now, in general, I showed you a couple of cases, but you have a lot of flexibility if you have the lasers available. So for example, the broadest frequency range that you can have pumping around 1 micron, that is the wavelength of an ytterbium laser, is around 7 micron if you employ a gain medium like lithium gallium sulfide. And you can have almost single cycle pulses also in that frequency range. So it's really a matter of finding the optimum condition and at the condition at which you want to operate. Other relevant materials that you can have for mid-infrared operation are LGS, silver gallium selenide, silver gallium sulfide, optically patterned gallium arsenide, gallium selenide, zinc telluride, and so on and so forth. So these are all, let's say, belong to the class of either low band gap dielectrics or semiconductors. Gallium arsenide does not allow to do phase matching, so you need to do the equivalent of periodic polling that is optically patterned. So you need to cut it and grow it with alternating domains. It's also possible to use organic crystals, a bit more controversial, honestly, but they are a quite large family, a bit more structured in their optical response. One famous member of these family is called DUST. I don't even remember what is the acronym for. In addition, you have, if you want to shoot for really short pulses in mid-infrared, you have another possibility. And this possibility is to maybe limit the bandwidth at the first step, so that you're able to extract as much energy as possible. So via DFG, you try to maximize the efficiency in the process while not caring excessively about the bandwidth. And then, as we have heard the talk before, you know, nonlinear broadening is always something that it's very useful, exploiting typically odd orders nonlinearities, like chi3. And you can do this broadening in semiconductors. Okay, and there are some examples in the literature in which you can exploit the propagation in a standard semiconductor to broaden the pulse in order to achieve, let's say, octave spanning spectra that translates in having the single cycle pulse that might be needed for your applications. Okay. Now, I want to make one final comment about phase matching related to the generation of spectral components in this frequency range. And then I will move to quickly a couple of examples of these pulses in modern research? Well, phase matching, it's a bit tricky. The more you move to the infrared, the more it's problematic for several reasons. You have always transition at some point in the mid-infrared in every material, so you're going to excite phonons. And to achieve this condition of energy momentum conservation, that it's typically done even in the visible or near infrared with birefringence, it's not always achievable for shorter frequency, for terahertz radiation, okay, for longer wavelengths. And the reason is that there is no material that allows good phase matching while preserving a very good nonlinear coefficient. So nowadays, the most intense terahertz pulses, let's say between, 50 to 200 microns, are generated in a completely different way. Are generated in a way that is more akin to the Cherenkov radiation. Cherenkov radiation comes from an accelerating electron moving in a certain direction, not accelerating, moving in one direction with a certain speed, and it's emitting radiation in a direction that is not the direction of propagation, and it's not orthogonal. And it's basically similar to the sonic boom that planes have when they overcome the speed of sound. At that wave, all the wavefronts interfere constructively, so you have a wavefront of radiation that propagates in that direction. This can be done also to achieve phase matching. So you can have an optical pulse that propagates in one direction, and you have phase matching for a direction in a different, for the emission of radiation in a different direction, while you maintain the matching of the wave vector between the new photons and the pulse that is generating the different frequency generation. Of course, this is cylindrical symmetric, so you're going to have a cone that is emitted and is going to generate radiation. And this, it's used for emitting terahertz radiation. So for example, you can easily use this method on lithium niobate, that is a material that is an extremely high nonlinear coefficient, to generate intense terahertz with this technique, so this Cherenkov-like radiation. The trick is that if you want to have efficient generation, and you don't want to disperse energy in a cone, you're going to degenerate this nonlinearity by using a pulse that is front tilted. So instead of propagating in the material with a bullet, you propagate with something that has a pulse front tilting. So it's intrinsically generating radiation with the maximum efficiency in the direction in which you want the emission of the terahertz. And this is extremely, it's also easy to achieve because you can use a grating and a dispersion from a grating to have the pulse front tilting that you want with the proper configuration of the grating itself. Okay, so this is all in general for the generation of mid-infrared and terahertz pulses. But the nice thing is that once you have this toolbox, you have this extreme advantage in having pulses that you can detect with extremely high precision in amplitude and phase. And also you can study with subcycle precision and manipulate with subcycle precision. So I show you just a couple of things that you can do in terms of pulse shaping at this frequency range. So this is an experiment that we did a few years back, in which we use a 20 micron pulse or multi-terahertz, whatever. Sometimes we call multi-terahertz because we call terahertz everything we can do the electro-optic sampling, but doesn't matter. It's exactly the same frequency range that you are discussing here. So if we take a germanium wafer, germanium is a semiconductor that is completely transparent to long wavelengths. It doesn't even have phonons because it's perfectly symmetric crystal. So there are no optical phonons in germanium that hinder absorption in the far infrared. So you can basically, it's like a window. You transmit completely, especially if you are at Brewster angle, okay? But what you can do is that you can shine a short near-infrared pulse onto the germanium wafer and make it metallic, okay? You excite free electrons by absorption of radiation. You excite free electrons in the in the semiconductor. When you have free electrons, you have a plasma frequency. If the plasma frequency is high enough, the semiconductors behave metallically up to that frequency. And we are able to create plasma frequencies up to a few microns. So we switch on the germanium wafer to be perfectly metallic. And basically this becomes a mirror, so you can reflect the radiation. And changing the delay between the two the switching pulse and the terahertz pulse, you can control between transmission and absorption. So you can say it's an optical gate, okay? But not only, thanks to the very good combination of the duration of the near infrared and the mid infrared, we can even do something more, that is slicing a pulse, okay? So if our switching occurs during the mid infrared pulse itself, we can slice up individual cycles of the optical radiation itself. And this is the experiment. So this is the pulse as it's fully transmitted by our germanium wafer. And this arrow that you see on top, it's the temporal arrival of our gating pulse that is switching on and off selectively the pulses. And then you could think about two of these arrangements and cut from both sides, for example. Okay, so you can do surgery on a sub-cycle level. This is even fancy, because in practice what we are doing is generating new frequencies. Even if it doesn't seem a method that intrinsically would lead to the generation of new colors, it's phase modulation, and as such is generating new colors there via mixing with the plasma that has been generated in the semiconductor itself. Even beyond that, it's possible to even shape the pulses to acquire very weird profile in the time domain. So for example, here you see that if you use a pulse like the red one, that is a terahertz pulse standard, you can cut it with such a short pulse that basically the new waveform has an abrupt and steep onset. Okay, so it becomes a wave, a shock wave in the terahertz frequency domain. And also in this case, you're going to generate way more frequencies that basically span from 0 to 60 terahertz. That means from 0, basically from 5 micron to, okay, whatever, hundreds of microns. And this is a peculiar way that you can deal with light, especially in the mid-infrared and far infrared spectral domains. I want to, I still have a few minutes. I want to close with just one example on how to apply these intense pulses to study, in particular, condensed matter, because lately there is a lot of excitement in the last few years about, let me see. Okay, let's start from here. So, a lot of excitement about generation of high harmonic generation in solids. And if we use mid-infrared, we are ideally suited in the frequency range to be non-resonant with the excitation of dielectrics and semiconductors. So, for example, if we use intense radiation, we can emit the harmonic spectrum. But we want it to be a little bit more precise. So we have this harmonic spectrum that is emitted when you illuminate with gallium arsenide sorry, the title here is a bit switched. When you illuminate gallium arsenide with intense mid-infrared radiation. But what happens to the material itself? Okay, we have the generation of radiation, but we have also something that is made by linear absorptions. So we can see the system as a standard semiconductor. So we have valence and conduction band. What happens when you apply an electric field? That can be optical, as in this case, okay? The non-resonant excitation of the material, it's like an electrical bias on the semiconductor. So what we can do is we bias the system. That means that we bend in the real space the band structure of the semiconductor, and we can have the so-called Franz Keldysh effect. So we can have absorption below gap, okay? What happens if we pump even more, if our field becomes stronger and stronger? Well, at that point, the alignment of the electronic level of each atoms that makes up the band structure will be lost. So every atom, you don't have anymore the periodicity along the direction in which you're applying the electric field to be able to define a band, okay? Because you don't have anymore the overlap between atomic orbitals. So you break them. So you start to have individual atomic lines on a single chain, okay? Because they cannot be delocalized anymore on the full chain. This is called the Wannier-Stark ladder that was not observed in bulk materials. And at extreme fields, you're going to disrupt the material completely and have simple atomic absorption. We did that experiment by basically illuminating at 10 micron, 20, 30 terahertz, a sample of gallium arsenide and probing resonant to the transition of gallium arsenide, that is 800 nanometer, with a pulse that is much shorter than the optical duration of the cycle. Okay, so we can observe what is the instantaneous effect of the field of the pulse that you're using to bias the material with a temporal duration that is much shorter than the optical cycle itself. And we have the generation of harmonics. And what we are doing is that we are looking at this kind of absorption in gallium arsenide, okay, this area spanning from 1.4 to 3 electron volt. And we did that with short pulses provided by optical parametric amplifiers. And this is what we observe. So this is the band gap of the material, okay, this vertical line. When we illuminate with the terahertz, we see that at the modulation of the terahertz, we have the Franz Keldysh absorption. So we have absorption below band gap, as I was describing before. And above, you have some modulation of the absorption at the periodicity of the terahertz of the mid-infrared. Here you see the details about this process. But what I want to show you is that after a certain level of field applied to the system, so if we crank up the intensity of the mid-infrared radiation, we start to have absorption, strong absorption above a certain level. So what happens is that indeed we are destroying the three-dimensional order of gallium arsenide. So we are moving from a three-dimensional gallium arsenide to a sequence of 2D layered materials in which the absorption is enhanced at higher frequencies. So we move spectral weight from lower energies to higher energies. And basically gallium arsenide becomes a layered material, okay, in which we disrupted the periodicity and the wave function only along one direction where we are applying the electric field. And that stronger field, this becomes even more clear. Okay, with this, I think I finish my question. Thank you very much, and I'm open for questions.